Good evening, all. I will share the slides for this week. Is the slides visible? I hope it is. So, good evening, all. Welcome to week 6 assignments of the NPTEL PMRF course Introductory Organic Chemistry II, August 2024, by Professor Harina Chakrapani and Professor Neeraja Deshaputre. Myself, Anisha Suresh, PMRF TA for this course from IIT Bombay. So, coming to summary of the week 6. In week 6, the chapters that were discussed were active methylene group, aldol and related reaction, and aldol reaction using specific enol equivalents. So now coming to active methylene groups, these sort of here the sort of 1,3 dicarbonyl compounds are known as active methylene group. So this group that is present at the center of this 1,3 dicarbonyl compound is known as the active methylene group. Its pK value will be less as the anion that will be formed will be stabilized by both of this carbonyl compounds. So as you can see here, once the proton is subtracted, this double bond will be forming, and this carbon-carbon double bond will break and it will lead to forming enol. So the here the enol form of the dienyl malonate is stabilized by conjugation. So here as you can see, this can undergo conjugation. This double lone pair on oxygen can shift here. This double bond will shift here, and this carbon-carbon double bond will break and lead to formation of an enolate. So here the enol form of diethyl malonate can be stabilized by conjugation. That is why here the pK values of this active methylene groups will be lesser. Also, here the enol form of diethyl malonate, it can be stabilized by formation of intramolecular hydrogen bonding between this carbonyl and the enol form, that enol OH that will be formed. And in the case of ketoaldehyde, as you can see here, it can undergo enolization. It will lead to formation of a six-membered species by formation of intramolecular hydrogen bond. So these two different stable enols undergo rapid interconversion by means of tautomerism. As you can see here, this OH will break, this double bond will shift, and it will lead to formation of an OH here. So this different stable enols will interconvert by tautomerism, by means of tautomerism. Now coming to the pK values, if we compare, so these are normal compounds. Like carboxylic acid, it will be more acidic and its pK value will be 5. When nitro compounds, because of the electron withdrawing effect of the nitro, its pK value will be around 9. In case of amide, this carbonyl group, its value will be so this hydrogen that is highlighted, that pK value will be around 15 because of the presence of this carbonyl. And aldehyde, so here this CH3, this proton pK will be around 17, and in case of ketone it will be around 20. Esters will have a pK around 25, and nitriles will have pK around 25. Amides like this will be having a pK around 30, and normal alkanes will have a higher pK of approximately 15. So in the case of active methylene groups, it will be having two electron withdrawing groups that can stabilize the conjugate base that will be forming, and hence the pK value of such active methylene groups will be lower. So compared to ketone, the beta diketone that is present here, this active methylene group's pK value is 9. Normal ketone, it is having a pK of 20. And now when we compare beta keto ester, its pK value is 11. Normal esters are having pK value of 25. And now when we consider beta diester, its pK value is 13. So here the pK values are drastically decreasing in the case of active methylene groups because of the presence of two electron withdrawing groups. Two dicarbonyl groups are present. That is the reason why its pK value is getting reduced. Now coming to cross condensation reaction. So normally in the aldol condensation reaction, previously we have seen about self condensation reaction. So in this cross condensation reaction, you can see two different compounds are there. One of this is having an enolizable hydrogen that is present, and the other one is not having any enolizable hydrogen. So that will undergo aldol reaction followed by elimination, leading to formation of this alpha beta unsaturated compound. So here the enolate will be forming, and that enolate will go and attack on this aldehyde, and further E1CB sort of elimination reaction will lead to this product. So for the cross condensation reaction to take place and to give this product as exclusively, the conditions that it should follow is one partner only must be capable of enolization. So if we consider these two partners, here this partner is only capable of enolization. The other partner that is shown here, it will not undergo enolization. Okay. The other partner must be incapable of enolization and be more electrophilic than the enolizable partner. So if it is having less electrophilicity than this enolizable partner, so then this can undergo self condensation reaction. So for avoiding that, we are making this aldehyde more electrophilic by introducing a nitro group, that is electron withdrawing group, making the sender more electrophilic, that the enolate will go and attack on the sender at a faster rate compared to that of the self condensation. Okay. Now coming to Cannizzaro reaction. So here also it is a sort of aldol condensation reaction, but the feature of this reaction is that here it will happen on aldehydes that are having no alpha hydrogen. So for aldol condensation reaction to take place, we have seen that it should have alpha hydrogen, right? So if alpha hydrogens are absent, and then aldol sort of reaction is taking place, that is known as Cannizzaro reaction. So it is a base catalyzed disproportionation reaction. So disproportionation reaction, you have seen that in the same compound, reduction as well as oxidation will be taking place. That is known as disproportionation reaction. So the aldehyde, on that the NaOH will be adding, so it will lead to formation of a tetrahedral intermediate like this. And when the oxygen it is falling back, this hydride will go and attack on another molecule of this benzaldehyde, leading to formation of a carboxylic acid double bond OH plus one alcohol. This is O minus. It can abstract proton from water upon hydrolysis, leading to formation of an alcohol. Clear? So this is Cannizzaro reaction. Now coming to aldol reaction in the presence of lithium enolates. So when we are having a carbonyl compound, when it is treated with LDA, that is lithium diisopropyl amine. So this is LDA. So when this ketone or carbonyl compound is treated with LDA, so the lithium can coordinate with the oxygen, lone pairs of oxygen, then it will form a cyclic transition state. Then the bond transfer will be like this: nitrogen will abstract the proton and this bond will shift here, the carbon carbon double bond will break, carbon oxygen double bond will break, and it will abstract the lithium, leading to formation of this lithium enolate. So this is the active species in the reaction. Now what will happen, we are having aldol reaction with a lithium enolate. So the electrophilic carbonyl compound forms a complex with the lithium atom. So this is the electrophilic carbonyl compound. So it will form a complex with lithium atom by form of this temporary bonding. Then this OLI bond will break. This carbon-carbon double bond will go and attack on this electrophilic center of this carbonyl, and this OLI bond will be forming, leading to formation of this intermediate. Now upon hydrolysis, the OLI bond will break and it will lead to formation of this beta hydroxy carbonyl compound. Is this clear? Now, the other reaction that we have studied was using silyl enol ethers, which is known as a Mukayama aldol condensation reaction. So here, in the presence of triethylamine and trimethyl silyl chloride, this carbonyl compound. So the triethylamine will abstract proton from here. Triethylamine will abstract the proton from here, and this will go and attack on trimethyl silyl chloride, and the chloride Cl minus will be leading to formation of the silyl enol ether. Now what will happen? We are having the silyl enol ether, and this is our electrophilic coupling partner. So the electrophilic coupling partner, in the presence of the Lewis acid, it will be activated. So TiCl4, whichever we are using, is the Lewis acid. So it will activate this electrophilic coupling partner. So then this carbon oxygen bond will be forming. This bond will this carbon carbon bond will go and attack on this electrophilic carbon center, and this positive charge on the oxygen will be neutralized, leading to formation of this intermediate. Now Cl minus, it will be having affinity towards silicon. It can abstract the silicon and neutralizes positive charge on oxygen. Now TiCl4 will be regenerated, and the O minus, it will go and attack on SiMe3, and the Cl minus will leave, leading to formation of this protected alpha hydroxy ketone. And this upon workup, when we are doing aqueous workup, OH will be generated. Okay, this is how silyl enol ethers will undergo aldol reaction. This is clear, right? Now coming to Reformatsky reaction. So here zinc enolites are involved. So here what will happen? The lone pair on zinc will add on to oxygen. This carbon oxygen bond will break, it will shift here, and this bromide will leave. So here a positive charge on zinc will be there, and the bromide will be acting as the counter anion. So zinc enolate is generated. Now what will happen in the presence of this electrophilic coupling partner, that this will coordinate with the zinc, leading to formation of this intermediate. Then OZ bond will break, and this carbon-carbon double bond will go and attack on the electrophilic carbon center, and this OZ bond will be forming. So this intermediate will form, which upon workup will lead to formation of this beta hydroxy ester. Okay. So this is Reformatsky reaction. Now coming to Asa enolates. So we have seen reactions involving formation of imines, enamines and all. So here we are having a primary amine and an aldehyde. In the presence of a acid or Lewis acid, it will lead to formation of the imine. Now when we use a base like LDA, LDA can abstract this alpha proton, lead to formation of this Asa enolate. Okay. This is known as Asa enolate. Now what will happen? We are having the electrophilic and enolizable aldehyde, and this this can coordinate with this lithium, leading to formation of the six-membered sort of transition state, and this NLI bond will break, and this carbon-carbon double bond will go and attack on this electrophilic center of this aldehyde, and this OLI bond will be forming, leading to formation of this lithium alkoxide. First formed product contains imine and the lithium alkoxide. Okay, so the lithium alkoxide and the imine is here. Now what will happen when we are treating with H plus and water? This OLI will be converting into OH, imine alcohol, and then imine hydrolysis will take place. This imine will convert into aldehyde, and upon dehydration, condensation reaction will take place, and we will get this final alpha beta unsaturated carbonyl compound. Okay, this is the reaction with acetylolates. Now, for further references, you can follow Claydon Organic Chemistry chapters 21, 26, and 27 for aldol and related reactions. Now, coming to our problem solving session. So, this is the question number 1. Predict the major product of the following reaction. So, a carbonyl compound is there, a bromide, and zinc is given. So, what sort of reaction is taking place here? Hello? We have seen some aldol reactions. So, which sort of aldol reaction is taking place here? So, since zinc is involving, we know it is Reformatsky reaction. So, out of this four options, what is the right option? Hello? So, let us see the mechanism. So, in the presence of this bromide, the zinc will insert into this bromide as we have like Grignard reagents. So, the zinc will get inserted, and that so here this sender will be having partially positive charge, and this will be having partially negative charge. So, this will go and attack on this carbonyl sender, leading to formation of this intermediate, and which upon hydrolysis will lead to formation of this hydroxy compound. Okay. So the right option will be option A. Why you are not responding? Isn't it?
Madam, actually, I am in journey. That's why I place in mute. But I listen my class.
Okay, okay.
But actually, I am traveling from one area to another area.
Oh, no problem, no problem.
But in the earlier, you sent a link on Sunday. That's why we can respond. But today is
Okay.
a working day.
Sunday some trouble was there. That is why I
But
will.
today is a working day. We work in some other places. That is why we can't respond.
Yeah, yeah.
We are listening to your class.
Okay.
Try to understand.
Hmm. Sure, sure.
Okay.
So this is the answer for this question number 1, and here the name reaction that is taking place is Reformatsky reaction. Now coming to question number 2. So here, predict the structure of the enolate formed in the given reaction. So we are having a carbonyl compound, and it is treated with LDA, that is lithium diisopropyl amide. So what is the structure of the enolate that will be formed? So here we know that here a alpha proton will be present. So the LDA, that is lithium diisopropyl amide, will be abstracting this proton, leading to formation of the enolate. So here this is the mechanism. The nitrogen anion on LDA will be abstracting this alpha hydrogen. So here this bond will shift here, leading to formation of carbon-carbon double bond, and this carbon-oxygen double bond will break, leading to formation of the enolate. So this is the enolate that is forming, and it will lead to formation of this amine as the byproduct. So the right option will be option C. Clear? Okay. Now coming to question number 3. Find out the correct product of the following reaction. So we are having an aldehyde and a ester, anhydride here, and it is treated with ACONA, NaOAC, and heated. So what will be the product that will be forming in this reaction? So let us see the mechanism. So this anhydride, this is having a this will be having alpha hydrogens. So NaOAC, it will be existing like Na plus OAC minus. So this will be a good base that will abstract this proton, leading to formation of this enolate. And this enolate, once it will fold, this O minus will fold, this carbon carbon double bond will go and attack on this electrophilic carbon atom of the aldehyde, leading to formation of this intermediate. Now what will happen, this O minus will go and attack on one of the this carbonyl group of the anhydride, and that will get shifted to this position. So trans-esterification sort of reaction is taking place here. So we will get this intermediate, and now this is sort of an active methylene group. As you can see, dicarbonyl groups are there, and this is the active methylene group that is present. So this OAC can abstract this proton, and it can lead to formation of this enolate. And once this enolate is falling back, even CB sort of mechanism will be taking place, removing this OAC minus. It can remove as acetic acid as well, because proton will be there in the medium. Okay, we will get this as the final product. So here the important step is formation of this active methylene species. This is active methylene. It's not fully active methylene because the carbonyl group is not present at this position. Okay, partially sort of active methylene. So here even CB will be taking place, and it will lead to formation of this aldol condensation product. So the right answer will be option B. Is this clear? Okay. Now coming to question number 4. Find the product of the following reaction. So two molecules of the aldehyde, it is reacting with KOH, and what will be the product that is formed. So when we are seeing this, we can come to know that there is no alpha hydrogen present in this compound. So the reaction that it will undergo is Cannizzaro reaction. Here no alpha hydrogens are present. So if Cannizzaro reaction is taking place, what will be the product that we will get? Yeah, alcohol and acid products will be forming, and option C will be the right answer. So the mechanism will be like the OH will add on to this electrophilic carbon center, leading to formation of this tetrahedral species. And once the O minus is falling back, the hydride will be removing, and it will go and attack on other molecule of the aldehyde, leading to formation of acid and alcohol. So it is a sort of base catalyzed disproportionation reaction. So option C is the right answer. Now coming to question number 5. So identify the major product of the given cross-aldol reaction. So similar sort of reaction was discussed in the lecture as well, I think. So here a substituted amine is given, and active methylene group is there, and this is the electrophilic coupling partner. So what will be the product that is forming? So let us see the mechanism. So that base, that is this amine, will be abstracting the active methylene proton. It will lead to formation of this enol or enolate. Then once it is falling back, it will go and attack on this electrophilic carbonyl of the electrophilic coupling partner, leading to formation of this intermediate. So again, one more proton is present there. So the base can abstract that proton, leading to formation of the enolate. Once it is falling back, this double bond will shift here, and this OH will be removing as water, leading to formation of this alpha beta unsaturated ester. Okay. So option A will be the right answer. Mechanism is clear, right? Okay. Now coming to question number 6. What would be the major product of the following reaction? So two molecules of cyclopropanone is reacting, and it is giving the aldol condensation product. So the mechanism will be like, so here they have forgot to mention the base, that is KOH. So in the presence of the base, the OH minus will be abstracting this alpha hydrogen. So this enolate will be resulting, and this enolate will go and attack on this carbonyl center, leading to formation of this intermediate. So here beta hydroxy ketone is resulted. So again, there is alpha hydrogen present. So the base, that is KOH, it can abstract this alpha hydrogen, leading to formation of the enolate. And once this will fall back, this double bond will shift here, and the OH minus will leave. That is E1CB sort of mechanism is taking place, and it will lead to formation of this aldol condensation product. So first aldol reaction will be taking place, giving this beta hydroxy ketone. Then again formation of enolate will take place, and the E1CB sort of elimination will take place, leading to formation of this alpha beta unsaturated ketone. So the major product that will be forming in this reaction is option A. Clear? Okay. Now coming to question number 7. For the sequence of reaction given below, so four options are given. Compound A is a lithium enolate. The second step is a benzylic acid rearrangement. The compound B has two aromatic rings. Compound A has two aromatic rings. So four statements are given. So out of which one of the statement is only correct. So you can see the reaction. So from the reaction arrows, you can come to know which of the statement is right. So the first compound A is a lithium enolate. That is false because it is forming zinc enolate. This is a Reformatsky reaction. So compound A is lithium enolate. It is false. It will be a zinc enolate. And second step is benzylic acid rearrangement, that is also false. So the enolate addition will be taking place. It is sort of aldol reaction only, so this is also wrong. Now compound B has two aromatic rings, compound A has two aromatic rings. So we will see which is the right answer. So compound A will be just a zinc enolate will be forming, so only one aromatic ring will be present in that. So compound A has two aromatic rings is false, and compound B has two aromatic rings, it will be the right answer. We will see it after seeing the mechanism. So Reformatsky reaction we have seen. So it is an organic reaction where aldehydes or ketone condenses with alpha haloesters using metallic zinc to form beta hydroxy esters. So this reaction will be taking place in the presence of alpha halo compounds. Okay. So here what will happen? The zinc will add on to this oxygen. This carbon oxygen bond will shift here and the bromide will leave, leading to formation of this zinc enolate. Now the electrophilic compound will add on to will coordinate with the zinc enolate, leading to formation of this transition state, and this bond will break, and this carbon carbon bond will go and attack on the electrophilic carbon, and O-Zn bond will form, leading to formation of this compound, and this upon hydrolysis will give the beta hydroxy ester. So coming to our compounds, we are having this compound. So zinc will add on to this oxygen, this bond will shift here, and this bromide will leave, leading to formation of this enolate. So this is our compound A, and this compound A is going to add on to this electrophilic aldehyde. So this will coordinate in this fashion, like six membered sort of transition state will be there. So this O-Zn bond will break, leading to formation of this bond here, and this carbon carbon bond will break and it will add on to this aldehyde, and this O-Zn bond will be forming here. So we will get this intermediate. Okay, and this upon hydrolysis it will give this compound B. So compound B is having two phenyl groups, that is aromatic groups. So compound B is having two aromatic groups is the, or two aromatic rings is the right answer. Is this clear? So this is the mechanism for Reformatsky reaction. Okay. So compound B has two aromatic rings is the right answer. Now coming to question number 8. So the structures of intermediate P and major product Q formed in the following reaction sequence are. So we are having a 2-methyl cyclopentanone and this pyrrolidine. So this is leading to formation of an imine in the presence of H plus. So that is the intermediate. Imine will be intermediate, and then that will undergo alkylation reaction in the presence of this alkyl bromide, and then imine hydrolysis will take place, leading to formation of the ketone. So we have to identify P and Q. C. Yeah, C will be the right answer. So here this less substituted um, sender will lead to formation of the enamine. So why we will discuss here. So here the Hoffman enamine will be forming in our case. So we are having bulky base. So this is sort of a bulky base compared to normal amines. So the use of a bulky amine to gain access to Hoffman product follow same rule as using a bulky base but for different reasons. So here we are having this ketone and it is treated with this amine, it will lead to formation of the Hoffman enamine. So that is the less substituted enamine will be formed compared to other one. So the reason is that when we compare this in the when we in the conformation, methyl not attached to double bond and may get out of the way sterically from the large amine group. So here the methyl group is not present on the double bond and hence it will not cause any steric hindrance with this amine. And in the case of this other product, the methyl group is attached directly to the double bond. It will have bad steric interaction with the large amino group. So if we are considering a cis alkene that is having bulkier groups, that sort of steric hindrance will be there in the case of this other product. So this Hoffman product will be formed in major. And states of amine, it will be formed when we are using small amines like this sort of small amines. If we are using, it will lead to formation of states of product, that is more substituted enamine will be formed in this case since steric hindrance will be less here. So a small amine group does have steric problems. As such, it will form the more substituted double bond which is stabilized by hyperconjugation to a greater extent than is Hoffman enamine double bond. Okay. So the more substituted double bond will be formed in the case of states of enamine, and in our case, since we are having a base or a amine like this which is more substituted or bulkier, so we are getting the Hoffman enamine. So that is why this enamine is forming in our case. Okay, so P will be this Hoffman enamine. Now this lone pair on an amine will fall and this carbon carbon double bond will go and attack at this sp3 center. Bromide will be leaving, leading to formation of this intermediate which upon hydrolysis aqueous workup or it will lead to formation of this ketone. Okay, so this is the P, that is Hoffman enamine, and this is the Q. Is it clear? Option A will be the right answer. Okay. Now coming to question number 9. Which of the following aldehydes will undergo a Cannizzaro reaction? So a formaldehyde is given, benzaldehyde is given, and tertiary butyl aldehyde is given. In all the cases, see, in all these cases, there is no alpha hydrogens present. So this is one of the condition for Cannizzaro reaction to take place. So all of the above will be the right answer. So Cannizzaro reaction is a chemical reaction that involves a base-induced disproportionation of two molecules of non-enolizable aldehyde to give a carboxylic acid and a primary alcohol. So as we have seen the mechanism, it will undergo a base mediated disproportionation reaction. So here we should have two molecules of non-enolizable aldehyde, that is it should not have any alpha hydrogens, and it will lead to formation of carboxylic acid and a primary alcohol. So what is disproportionation reaction means? It is a reaction in which the same element is simultaneously oxidized and reduced. Okay. So that is why here the in Cannizzaro reaction we will be having a aldehyde. So that is undergoing oxidation leading to formation of carboxylic acid and reduction leading to formation of alcohols. So the same molecule is getting oxidized and reduced. That is why it is known as a disproportionation reaction. Okay. So this is the mechanism for Cannizzaro reaction. We are having a non-enolizable aldehyde. So here the base cannot abstract any proton. So the base will undergo a nucleophilic addition leading to formation of this tetrahedral intermediate or hydrate anion. Since OH minus addition is taking place, it is leading to formation of the hydrate. So we will get this hydrate anion, and this upon deprotonation it can lead to formation of this dianion. Now what will happen when this is falling back, this hydride will go and attack on this carbonyl group leading to formation of this carboxylate anion and this alcohol. Normal NABH4 sort of reduction mechanism it is. Okay. So that is why all of these aldehydes can undergo Cannizzaro reaction, and all of the above will be the right answer. Now coming to question number 10. Write the correct order of reactivity of benzaldehydes given below to give the aldol product in presence of NaOH. So this is our enolizable compound and it is treated with NaOH. So we will get an enolate and it should react with any of this aldehydes. So what will be the reactivity order? So here what we should consider is that the aldehyde should be more electrophilic. More electrophilic the aldehyde is, more will be the reactivity. So which will be more electrophilic aldehyde?
A.
A will be more electrophilic aldehyde. So this will be having higher reactivity A. Now this methyl group and OMe group, it will be having inductive effect. It will donate electrons and hence this electrophilicity of this carbonyl will decrease. So A, then comes C. Okay. Since this is electron donating effect, then compared to OMe will have electron donating resonance effect as well as inductive effect. So then comes B, then comes D. Here electron donating resonance effect. It is more predominant in here. And here electron donating inductive effect. So this will be the right order of reactivity of this benzaldehydes. Is this clear? This is electron withdrawing resonance and inductive effect. So when we make the benzaldehyde more electrophilic, then it will undergo the reaction at a faster rate. So the presence of electron withdrawing groups can make the benzaldehyde more electron deficient or electrophilic. That is why this paranitro-benzaldehyde will be more reactive towards this aldol reaction. And this since it is having a electron donating group, that is OMe, so this will be having less electrophilic carbonyl at the center. That is why it will be having less reactivity. So option D is the right answer. Okay. Now coming to the next question. Hello, is my screen visible? Hello. Hmm. Sorry, there was some network issues. I will share the screen again. So coming to question number 11. So the major product formed in the following reaction is. So here we are having a dicarbonyl compound and we are treating it with KOH and methanol. So here the aldol condensation reaction will be intramolecular. Intramolecular aldol condensation reaction will be taking place. So what will be the major product that we will get? So let us see the mechanism. So this is the compound that we are having. So here these three are alpha hydrogen, these three are alpha hydrogen and these two are alpha hydrogen. So the base can abstract any of these protons and it will lead to formation of the enolates. But here majorly these protons will be abstracted and it will lead to formation of this enolate, and once it is falling back, this carbon-carbon double bond will go and attack on the other carbonyl, leading to formation of this OH here. Okay. So this product will be majorly formed. Here why this is forming majorly, because formation of six membered rings are more feasible than the formation of higher ring systems like 8 membered or 7 membered. Now again there will be proton present here. The base can abstract that proton, leading to formation of this enolate, and once it is falling back, even CB sort of elimination reaction will take place and it will lead to formation of this alpha beta unsaturated system. Okay. You can try working out the formation of the other products as well by formation of other enolates from this alpha hydrogen. But this is the major product that is getting formed. Okay. So option C is the right answer. Any doubts? Okay. Now coming to the last question in this session. So identify X and Y in the following reaction sequence. So this is our starting compound. It is treated with LDA, that is lithium diisopropyl amide. LDA. And it will lead to formation of X. Then that X will react with this carbonyl compound, leading to formation of Y. So what is X, what is Y? So this is also an example of aldol reaction. So this is the alpha hydrogens that are present. So LDA can abstract that alpha hydrogens, leading to formation of this enolate, lithium enolate. So this lithium enolate is our X. Now this O minus will fall here and this carbon-carbon double bond will go and attack on this carbonyl carbon, and this carbon-oxygen double bond will break, leading to formation of O minus. So that upon abstraction of proton or hydrolysis, it can lead to formation of this beta hydroxy ketone. So that is Y. So first formation of the lithium enolate will take place in the presence of LDA, and then It will add on to our electrophilic carbon center, leading to formation of the beta hydroxy ketone. So the aldol condensation reaction is taking place here. Sorry, aldol reaction is taking place here using lithium enolates. So option A is the right answer. Okay. So here majorly you have to work out each of the mechanisms so that it will be easier for you while attending exams. Most of the mechanisms are similar only. Is there any other doubts based on any questions that we discussed today or based on the lectures? Okay. There are no doubts. We can wind up today's session. Thank you all. Thank you.